Badlands National Park. National Parks of the United States. To understand Badlands National Park is to understand the relentless power of erosion acting upon the deep history of the North American continent. Located in southwestern South Dakota, roughly 75 miles east of the granitic uplift of the Black Hills, this park represents one of the most striking geological landscapes on Earth. It is a place of sharp contrasts, where a flat, wind-swept, mixed-grass prairie suddenly gives way to a chaotic, rugged terrain of gullies, buttes, pinnacles, and spires. These geological formations, characterized by their banded colors of red, orange, tan, and white, form a jagged scar across the Great Plains, a landscape so inhospitable and seemingly broken that it has deterred travel and settlement for centuries. Yet within this desolation lies a fossil record of immense scientific value and a resilient ecosystem adapted to extremes. The park protects over 240,000 acres of this terrain, preserving not only the scenic geological Badlands, but also the largest protected expanse of mixed grass prairie in the United States. The identity of Badlands National Park is dualistic. It is at once a geological graveyard, holding the mineralized remains of ancient mammals that roamed a long-vanished subtropical savanna, and a living, breathing wilderness where modern species fight for survival in a semi-arid climate. The park consists of two primary units: the North Unit, which houses the park headquarters, the Cedar Pass area, and the famous Badlands Loop Road, and the South Unit, or the Stronghold District, which is located within the Pine Ridge Indian Reservation and is co-managed by the National Park Service and the Oglala Lakota tribe. This partnership highlights the deep cultural significance of the land, which has been part of the Lakota heritage for generations. The name itself is a translation of the Lakota phrase Makosika, meaning land bad, a literal description of the terrain's lack of water, treacherous topography, and extreme temperatures. French-Canadian fur trappers who passed through the region in the 18th century echoed this sentiment, calling it les mauvaises terres à traverser, or bad lands to cross. Geologically, the Badlands are a textbook example of deposition followed by erosion. The story begins not with the jagged peaks seen today, but with a shallow inland sea. Approximately 75 to 69 million years ago, during the late Cretaceous period, the western interior seaway stretched from the Gulf of Mexico to the Arctic Ocean, bifurcating the North American continent. The bottom of this sea accumulated vast amounts of black mud, which eventually compressed into the Pierre Shale. This distinctive black shale forms the basement of the Badlands. It is rich in marine fossils, including ammonites, baculites, and large marine reptiles like mosasaurs and plesiosaurs. Although the Pierre Shale is the oldest formation exposed in the park, it is often obscured by the more colorful layers above it, visible primarily in the lower elevations and erosional slumps, where the overlying rock has been stripped away. Following the retreat of the western interior seaway, the region underwent a dramatic transformation. The uplift of the Rocky Mountains and the Black Hills to the west altered the drainage patterns of the continent. The climate shifted from a marine environment to a warm, humid, subtropical jungle. This era, the late Eocene, occurred roughly 37 to 34 million years ago. During this time, the soil weathered into a bright yellow color, creating what is now known as the Yellow Mounds. These mounds are actually paleosols, or ancient fossilized soils. The vibrant yellow and purple hues of these mounds stand in stark contrast to the gray and tan layers above and below them. marking a distinct boundary in the geological timeline. The yellow mounds represent a period of relative stability, where soil could develop before being buried by subsequent floods and sediments. Above the yellow mounds lies the Chadron Formation, deposited between 37 and 34 million years ago. By this time, the environment had shifted from a dense jungle to a floodplain system with meandering rivers. The sediment deposited here is largely gray in color and is composed of clay, silt, and sand, washed down from the eroding Black Hills. The Chadron Formation is significant for its fossil content, particularly the remains of the Titanothere, or Brontothere. These massive rhinoceros-like animals possessed distinctive Y-shaped horns on their snouts and roamed the ancient floodplains in great numbers. The presence of alligator fossils in this layer confirms that the climate remained substantially wetter and warmer than it is today, supporting a lush habitat that differs radically from the current arid landscape. The most iconic visual feature of the Badlands, the striated or banded cliffs, belongs primarily to the Brule Formation. Deposited during the Oligocene epoch, approximately 34 to 30 million years ago, this layer records a drying climate. As the continent continued to cool and dry, the lush forests gave way to open savannas. The Brule Formation is subdivided into the lower Orellan and upper Whitneyan members. The alternating bands of reddish brown and tan mudstones and siltstones, visible in the Brule Formation, were laid down by slow-moving streams and episodic flooding, as well as by wind-blown dust, known as loess. This era, often called the Golden Age of Mammals, saw the evolution of diverse fauna, including three-toed horses, tiny deer-like creatures, camels, and the ubiquitous oreodonts. Oreodonts, roughly the size of sheep but taxonomically distinct, are so common in these layers that the Brule Formation was historically referred to as the turtle oreodont layer. The abundance of fossils here makes the White River Badlands one of the richest Oligocene fossil beds in the world. Topping the geological sequence in the park is the Sharps Formation, the youngest of the major sedimentary layers, deposited between 30 and 28 million years ago. Composed of light-colored sandstone and siltstone, the Sharps Formation forms the rugged, caprock peaks that protect the softer layers beneath. This layer represents a continuation of the drying trend, with river channels becoming more entrenched and the landscape dominated by hardy grasses and scrub. Volcanic activity further west, in what is now Nevada and Utah, contributed significant amounts of ash to the atmosphere, which settled over the Badlands region. This volcanic ash is chemically unstable. Over millions of years, it has weathered into bentonite clay. Bentonite is a fascinating and structurally problematic material. When dry, it is hard and popcorn-like in texture, but when wet, it absorbs water and expands significantly, becoming a slick, sticky gumbo. This expansion and contraction cycle causes the surface to crack and crumble, preventing deep plant root penetration and accelerating the rate of erosion. The primary architect of the Badlands is erosion. The deposition of these sedimentary layers ceased roughly 28 million years ago, but the excavation of the Badlands did not begin until much later, approximately 500,000 years ago. In geological time, this is a remarkably recent event. The Cheyenne, White, and Bad Rivers began to cut into the high plains, stripping away the sediment and carving the fantastic shapes visible today. The erosion rate in the Badlands is staggering, averaging about 1 inch of material lost per year. This is a rapid pace for geological processes. At this rate, the Badlands as we know them will be completely eroded away in another 500,000 years. The mechanisms of erosion are primarily water and frost. Rainstorms in the region are often brief but violent, leading to flash floods that scour the soft sedimentary rock. Because the vegetation is sparse and the bentonite clay inhibits water infiltration, the runoff is immediate and destructive, cutting deep channels and gullies. Frost wedging also plays a critical role. Water seeps into cracks in the rocks, freezes, and expands, shattering the stone and creating the piles of scree found at the base of the cliffs. While the geology defines the topography, the biological reality of the Badlands is defined by the mixed grass prairie. This ecosystem is a transitional zone between the tall grass prairies of the deeper Midwest and the short grass prairies of the arid West. It is a landscape of resilience adapted to survive drought, fire, and extreme temperature fluctuations. The dominant plant life comprises various grasses, including western wheatgrass, needle and threadgrass, blue grama, and buffalo grass. These plants possess extensive root systems that can reach several feet underground, allowing them to access moisture deep within the soil and anchor the earth against the constant wind. The interplay between the prairie and the geological badlands is a dynamic struggle. The sod tables, flat-topped mesas covered in grass, are remnants of the original prairie floor that have not yet been eroded away. As the cliff edges recede, the prairie is literally undermined, collapsing into the gullies below. The flora of the Badlands is not limited to grasses. In the wetter gullies and along the seasonal watercourses, shrubs and trees such as the Rocky Mountain juniper and the Plains cottonwood can be found. The presence of trees is strictly limited by water availability. The juxtaposition of the white, barren rock and the vibrant green of the juniper creates one of the park's most striking aesthetic contrasts. Wildflowers also punctuate the prairie, blooming in succession from spring to autumn. The pasca flower appears early, sometimes pushing through late snows, followed by wallflowers, prairie violets, and the mariposa lily. In the heat of summer, the prickly pear cactus blooms, its yellow and pink flowers offering a burst of color in the sun-baked terrain. These plants have evolved mechanisms to conserve water, such as waxy cuticles, fine hairs to trap moisture, and reduced leaf surface areas. The fauna of Badlands National Park is as resilient as the flora. The park is home to a restored population of the American bison, the largest land mammal in North America. Once numbering in the tens of millions, bison were driven to the brink of extinction in the late 19th century. The introduction of bison to the Badlands has been a conservation success story. Today, a herd of approximately 1,000 bison roams the wilderness area of the park. These massive grazers are a keystone species for the prairie ecosystem. Their grazing habits create a mosaic of grass heights, which benefits various bird species, and their wallowing creates depressions that hold temporary water, supporting amphibians and insects. The bison is well adapted to the extremes of the Dakota climate. Their thick winter coats allow them to withstand blizzards, while their massive heads are used as snowplows to access buried forage. Sharing the grazing duties with the bison is the bighorn sheep. The subspecies found here, the Rocky Mountain bighorn sheep, was introduced to replace the extinct Audubon's bighorn sheep that originally inhabited the area. These animals are masters of the rugged terrain, their specialized hooves allowing them to scale the near-vertical sedimentary walls to escape predators and access mineral licks. The bighorn sheep are often seen on the pinnacles and precipices of the Badlands Wall, a 100-mile-long escarpment that serves as the spine of the park. The population is carefully monitored, as they are susceptible to diseases such as pneumonia, which can be transmitted by domestic sheep and goats. Perhaps the most ecologically significant animal in the park is the black-tailed prairie dog. Often misunderstood as a pest, the prairie dog is arguably the most critical keystone species of the mixed grass prairie. Prairie dogs live in vast underground colonies called towns, which can span hundreds of acres. Their burrowing activity aerates the soil, reversing the compaction caused by large grazers and allowing water to penetrate deeper into the earth. This results in vegetation around prairie dog towns that is often higher in nutritional value than the surrounding grass. Furthermore, the prairie dog serves as a primary food source for a multitude of predators, including coyotes, badgers, bobcats, golden eagles, and hawks. Their burrows provide shelter for species ranging from burrowing owls to rattlesnakes. Without the prairie dog, the complex food web of the Badlands would collapse. The dependence on the prairie dog is most critically exemplified by the black-footed ferret. This small, weasel-like carnivore is one of the most endangered mammals in North America. For years, the species was thought to be extinct until a small population was discovered in Wyoming in the early 1980s. Badlands National Park has been a primary site for the reintroduction of the black-footed ferret. These nocturnal hunters rely almost exclusively on prairie dogs for food and use their burrows for shelter. The survival of the ferret is inextricably linked to the health of the prairie dog population. However, both species face a significant threat from sylvatic plague, a flea-borne bacterial disease that can wipe out entire colonies. Park biologists engage in intensive management strategies, including dusting prairie dog burrows with flea powder and vaccinating ferrets, to maintain a viable population of this elusive predator. Predators in the park also include the swift fox, a small, house cat-sized fox that was once common across the Great Plains. After disappearing from the state, they were reintroduced to the park and the surrounding national grasslands. The swift fox is nocturnal and relies on speed to capture insects, small mammals, and birds. Their return adds another layer of restoration to the prairie ecosystem. Larger predators like the coyote are frequently seen trotting across the flats or hunting in the margins of the prairie dog towns. While mountain lions pass through the area, they are transient visitors rather than permanent residents, as the open terrain offers little cover for their ambush style of hunting. Bird life in the Badlands is diverse, comprising both prairie specialists and cliff-dwelling species. The cliffs and spires provide ideal nesting sites for raptors. Golden eagles are the apex aerial predators, soaring on the thermal currents rising from the heated rock. Prairie falcons and ferruginous hawks also patrol the skies. On the ground, the western meadowlark, with its distinctive yellow breast and melodic song, is a common sight and sound. The burrowing owl, a small, long-legged owl that nests in abandoned prairie dog burrows, is a favorite among birdwatchers. These owls are active during the day, unlike most of their kin, and can often be seen standing sentinel on the mounds of dirt outside their homes. Reptiles are well represented in the semi-arid environment. The prairie rattlesnake is the only venomous snake in the park. It plays a vital role in controlling rodent populations. These snakes are ectothermic, relying on external heat sources to regulate their body temperature. In the Badlands, they are often found sunning themselves on the warm rocks in the morning or evening. During the heat of the day, they retreat into crevices or burrows to avoid overheating. Other reptiles include the bull snake, a large constrictor that mimics the rattlesnake's behavior, and the eastern yellow-bellied racer. The shorthorn lizard, often called a horny toad, is a master of camouflage, blending perfectly with the pebbled soil of the prairie. The climate of the Badlands is characterized by its volatility. It is a continental climate, far removed from the moderating influence of the oceans. Summers are hot and dry, with temperatures frequently exceeding 100 degrees Fahrenheit. The sun beats down on the light-colored rock, creating a dazzling and intense heat. Winters are long and bitterly cold, with temperatures plunging well below zero. The lack of tree cover means there is no windbreak. The wind is a constant presence, sculpting the snow into drifts, and drying out the vegetation. Precipitation is scant, averaging about 16 inches per year, with the majority falling in the spring and early summer. Violent thunderstorms are common in the summer months, bringing lightning, hail, and the heavy rains that drive the erosional processes. One of the less visible but equally fascinating geological features of the park is the presence of clastic dikes. These are vertical sheets of rock that cut through the horizontal sedimentary layers. They appear as thin, protruding walls, often harder than the surrounding rock. The origin of these dikes is a subject of geological debate, but the prevailing theory is that they were formed when tension cracks opened in the sediment and were filled with sand and silt washed in from above. Over time, this infill hardened into sandstone. As the softer mudstone around them eroded, the clastic dikes were left standing in relief. They provide a visual record of the stresses and strains the land has undergone over millions of years. The Badlands are also a place of silence and darkness. The remoteness of the park, far from major urban centers, ensures that light pollution is minimal. The night sky over the Badlands is a sprawling canopy of stars, offering some of the best stargazing in the country. The Milky Way appears as a distinct, bright band across the heavens. This darkness is an integral part of the park's wilderness character, allowing nocturnal animals to function without the disruption of artificial light. Similarly, the natural soundscape is preserved. Without the noise of traffic or industry, the sounds of the wind in the grass, the call of the coyote, and the bark of the prairie dog become the dominant auditory experiences. The human history of the Badlands is as layered as its geology. Paleo-Indians inhabited the region as early as 11,000 years ago, hunting mammoths and ancient bison. Throughout the millennia, various cultures utilized the area for hunting and seasonal camps. The Arikara people lived in the region before being displaced by the Lakota in the 18th century. For the Lakota, the Badlands were not just a hunting ground, but a spiritual landscape. The south unit of the park, specifically the Stronghold Table, was the site of one of the last ghost dances in 1890. The ghost dance was a spiritual movement that swept across Native American tribes in the late 19th century, promising the return of the buffalo and the disappearance of the white settlers. The U.S. Army's suppression of this movement culminated in the Wounded Knee Massacre, located just south of the current park boundaries. The co-management of the South Unit today is a recognition of this painful history and a step toward integrating indigenous perspectives into land management. Homesteading in the early 20th century brought a new wave of human interaction with the land. The harsh conditions made traditional farming nearly impossible, and many homesteaders failed, leaving behind sod houses that quickly dissolved back into the earth. However, ranching proved more sustainable, and the culture of the American West remains deeply embedded in the communities surrounding the park. The transition from open range to protected parkland was a slow process. The area was designated a national monument in 1939 to protect the fossil resources and the unique scenery. It was not until 1978 that it was redesignated as a national park, a change that reflected the broader recognition of the value of the mixed grass prairie ecosystem and the need for deeper wilderness protection. Paleontological research in the park is an ongoing and rigorous scientific endeavor. The Badlands are not a static museum. As erosion reveals new layers, new fossils are constantly being exposed. Paleontologists working in the park must race against the elements to excavate specimens before they are destroyed by the very forces that revealed them. The Fossil Preparation Lab at the Visitor Center allows the public to witness the delicate process of removing the rock matrix from the fossilized bone. This scientific work helps to refine our understanding of the Eocene and Oligocene epochs, offering insights into how mammals evolved in response to climate change. The shift from jungle to savanna recorded in the rocks serves as a potent analog for understanding modern climate dynamics. The specific mechanism of fossilization in the Badlands relies on the rapid burial of remains. During the floods of the Oligocene, animals that drowned or died near the riverbanks were quickly covered in sediment. This anoptic environment prevented scavengers from scattering the bones and slowed the decomposition process. Over time, groundwater rich in silica percolated through the sediment. The silica replaced the organic material of the bone molecule by molecule, turning it into stone. This process, known as permineralization, preserves the delicate structures of the bone, allowing scientists to study the anatomy of these ancient creatures in minute detail. The White River Group, the collective name for the Chadron, Brule, and related formations, is the standard reference for terrestrial Eocene-Oligocene fossils in North America, making the park a site of global scientific importance. Conservation in Badlands National Park involves active management of invasive species. Plants such as Canada thistle and yellow sweet clover threaten to outcompete the native grasses. Park staff utilize controlled burns, herbicides, and mechanical removal to keep these invaders in check. Fire management is a critical aspect of prairie health. Historically, lightning-caused fires swept through the plains regularly, clearing out dead vegetation, recycling nutrients into the soil, and preventing the encroachment of woody shrubs. The suppression of fire in the 20th century led to an unhealthy buildup of fuel. Today, prescribed fire is used as a tool to mimic these natural disturbances, ensuring the vigor of the wheatgrass and needle and threadgrass that sustain the bison and elk. The Badlands Loop Road provides the primary conduit for visitors to experience these geological and ecological wonders. It winds through the eastern portion of the park, offering overlooks that showcase the different formations. At Big Badlands Overlook, the view stretches east toward the rising sun, illuminating the intricate drainage patterns of the White River Valley. At Pinnacles Overlook, the high vantage point allows one to see the transition from the grassy tables of the upper prairie down into the chaotic, eroded wilderness of the Sage Creek Basin. The road itself is an engineering feat, traversing the unstable bentonite clays and requiring constant maintenance to prevent it from sliding down the hill. The wilderness area within the park, particularly in the Sage Creek unit, offers a different experience. Here, there are no paved roads or marked trails. Hiking is cross-country, following bison paths or dry creek beds. This allows for a profound sense of solitude and immersion in the landscape. Navigating this terrain requires an understanding of the topography. The landmarks can change appearance rapidly as the light shifts. The solitude of the wilderness area is essential for the breeding success of sensitive species and provides a sanctuary where the natural processes of predator and prey can play out undisturbed. Water remains the limiting factor and the defining force. The White River, which flows along the southern boundary of the park, carries a heavy load of dissolved, light-colored clay, giving it a milky appearance. This river is the primary drainage for the region. Within the park, water is ephemeral. Rainwater collects in natural depressions called potholes, but these are often temporary. The wildlife has adapted to this scarcity. Mule deer and pronghorn are capable of traveling long distances to find water. Plants go dormant during drought, turning brown and brittle, only to green up rapidly with the first significant rain. This boom and bust cycle of moisture drives the rhythm of life in the Badlands. The aesthetic power of the Badlands lies in its ever-changing nature. The soft, sedimentary rock erodes so quickly that the landscape is literally reshaping itself in human time. A spire that stands today may be toppled by a storm next year. A fossil hidden for 30 million years may be exposed tomorrow, only to be washed away the following week if not discovered. This transience imparts a sense of urgency and fragility to the stone. The colors, too, shift with the light and moisture. After a rain, the bands of red and purple intensify, becoming vibrant and saturated. In the harsh midday sun, the landscape bleaches out to blinding whites and tans. At sunset, the shadows lengthen, throwing the relief of the gullies into sharp contrast and turning the rock to shades of gold and crimson. The park also serves as a laboratory for studying the effects of climate change on grasslands. As temperatures rise and precipitation patterns become more erratic, the balance between cool season grasses like western wheatgrass and warm season grasses like blue grama may shift. This could have cascading effects on the bison and other grazers. Scientists monitor vegetation plots to track these changes, using the park as a baseline for the health of the northern Great Plains. The geological formations known as sod tables are particularly interesting features. These are isolated remnants of the prairie that have been cut off from the main tableland by erosion. They stand like islands in a sea of badlands. Because they are often inaccessible to large grazers like bison, they can harbor relict plant communities that have not been subjected to grazing pressure. These tables provide a glimpse into what the pristine prairie composition might have looked like before the reintroduction of heavy grazing. However, as the edges of the tables erode, the surface area shrinks, eventually dooming the plants on top to fall into the abyss. In the world of geology, the contact between layers is crucial. The unconformity is a surface where rock layers are missing due to erosion or non-deposition. In the Badlands, the contact between the Pierre Shale and the overlying yellow mounds represents a significant gap in time, a period where the Cretaceous Sea had retreated, and the land was exposed to weathering before the Eocene sediments began to accumulate. Understanding these gaps is as important as understanding the layers themselves, as they represent the missing pages of the geological history book. The mammalian paleontology of the White River Badlands also includes the ancestors of modern carnivores. The hyenodon was a creodont, a group of carnivorous mammals that are now extinct. It had powerful jaws capable of crushing bone and was a dominant predator of the Oligocene. Alongside it lived the Dinextrachus, a false saber-toothed cat. These predators hunted the herds of oreodonts and three-toed horses, Mesohippus. The Mesohippus was only about 2 feet tall at the shoulder, a far cry from the modern horse, and browsed on leaves rather than grazing on grass. The evolution of the horse in North America is well documented in the Badlands strata, showing the gradual adaptation of teeth and limbs to a changing environment. The park's management actively engages with the public to foster stewardship. The Junior Ranger program educates children about the value of fossils and the importance of leaving them in place. Theft of fossils is a significant issue. Taking a fossil from a national park is a federal crime. When a fossil is removed from its context without scientific documentation, the information it holds about the specific layer and location is lost forever. The park emphasizes in situ preservation, or professional excavation. The auditory environment of the Badlands is characterized by the wind. It whistles through the spires and rustles the dry grasses. This wind is a geologic agent, carrying sand and silt that sandblasts the rock faces. It is also a biological agent, dispersing seeds and drying out the soil. The silence of the Badlands, punctuated by the wind, is often cited by visitors as one of the most memorable aspects of their experience. In a world increasingly filled with anthropogenic noise, the acoustic purity of the Badlands is a rare resource. The intricate relationship between the geologic foundation and the living skin of the park creates a unique biome. The clays derived from the breakdown of the Sharps and Brule formations create soils that are high in mineral content, but challenging for plant growth due to their texture and shrink swell capacity. Only specific plant communities can tolerate these conditions. This edaphic, soil-related control of vegetation results in the patchy appearance of the landscape, where barren slopes sit right next to grassy swales. As one traverses the park from the wall down to the lower prairie, the sense of scale is distorting. The pinnacles can appear massive from a distance, but upon approach, the intricate detailing of the erosion becomes visible: tiny channels, miniature arches, and delicate hoodoos. Hoodoos are spires of soft rock topped by a harder caprock that protects the column from erosion. They are common in the Badlands and often take on bizarre, statuesque shapes. The story of the Badlands is ultimately a story of time. Deep time is recorded in the layers of the earth, measuring millions of years of deposition and evolution. Ecological time is measured in the cycles of the seasons, the migration of the bison, and the lifespan of the prairie dog. And erosional time is measured in the steady, relentless crumbling of the rock. These time scales intersect in this specific place, creating a landscape that is ancient, yet constantly renewing itself. The Badlands are not a dead wasteland, but a dynamic, high-energy environment where the forces of nature are laid bare for examination. The intersection of this immense geological timeline with the human experience creates a narrative that is far more complex than the simple visual spectacle of erosion. While the rocks speak of epochs spanning millions of years, the surface of the Badlands bears the imprint of thousands of years of human habitation, adaptation, and spiritual reverence. The transition from a purely geological understanding to a cultural and ecological one requires shifting the focus from the bedrock to the thin, fragile skin of soil and life that clings to it, and to the people who have navigated this treacherous terrain for millennia. The harsh beauty of the White River Badlands has acted not only as a barrier to travel, but as a sanctuary, a fortress, and a cathedral, shaping the cultures that encountered it just as the wind shapes the stone. The human history of Badlands National Park is most deeply and inextricably linked to the Oglala Lakota people. While the park's northern unit is the most visited, the south unit, or Stronghold District, offers a profound connection to Lakota heritage. This land is managed in a unique partnership between the National Park Service and the Oglala Sioux tribe, a relationship that acknowledges the sovereignty of the tribe and the sacred nature of the landscape. The centerpiece of this area is Stronghold Table, a high, grass-covered mesa isolated by sheer cliffs and deep ravines. Geographically, it is a natural fortress, accessible only by a narrow land bridge. In the winter of 1890, this table became the refuge for a band of Lakota practicing the ghost dance. The ghost dance was a messianic movement that originated with a Paiute prophet named Wovoka, who prophesied that if the indigenous peoples lived peacefully and danced a specific round dance, the white settlers would disappear, the ancestors would return, and the decimated buffalo herds would be restored. For the Lakota, facing starvation, disease, and the destruction of their traditional way of life, this message offered a desperate hope. They retreated to the Stronghold Table to dance without interference from the U.S. Army or the Indian agents who viewed the movement as an uprising. The geography of the stronghold allowed them to survive in the bitter cold, utilizing the natural springs and the grazing on the tabletop for their ponies. The archaeological footprint of this event is light but significant. There are no grand structures, but the spiritual resonance of the place is palpable. The eventual surrender of the dancers and the subsequent massacre at Wounded Knee, located just south of the park boundaries, marks the tragic conclusion of the Indian Wars, making the Stronghold District a landscape of mourning and remembrance. Long before the arrival of the Lakota in the 18th century, the Badlands were utilized by a succession of cultures dating back to the Paleo-Indian period. Archaeologists working in the park have uncovered evidence of human presence stretching back 11,000 years. These early inhabitants were nomadic hunters who followed the herds of megafauna that thrived at the end of the Pleistocene epoch. Distinct from the paleontological resources, which are millions of years old, the archaeological resources include hearths, lithic scatters, and kill sites found in the eroding terraces of the White River. The geography of the Badlands played a strategic role in prehistoric hunting. The steep cliffs and blind canyons could be used as buffalo jumps or traps. By stampeding a herd toward a precipice or into a confined gully, hunters could harvest large quantities of meat with relatively low risk. This technique required a sophisticated understanding of animal psychology and terrain. The eroding landscape poses a unique challenge for archaeology. Artifacts are constantly being exposed and then washed away. A hearth that has remained buried for 3,000 years might be visible for only a single season before falling into a ravine. This ephemeral nature of the archaeological record necessitates constant monitoring and demonstrates that the history of human occupation is being erased by the same forces that created the landscape. Traditional ecological knowledge held by the Lakota and other tribes provides a critical lens for understanding the plant life of the Badlands. To the untrained eye, the prairie might look like a monoculture of grass, but it is actually a pharmacopoeia and a grocery store. Ethnobotany, the scientific study of the relationships between people and plants, reveals that the flora of the Badlands supported a complex subsistence strategy. One of the most important plants is the prairie turnip, or Sorleia esculenta, known to the Lakota as tinsila. This legume produces a starchy tuber roughly the size of a hen's egg. It lies dormant underground for much of the year, sending up a flower stalk in the late spring. As the plant matures, the stem dries and breaks off, tumbling across the prairie to disperse seeds, but the tuber remains. Indigenous women would use digging sticks to harvest the root, which could be eaten fresh, boiled, or dried, and ground into flour for winter storage. The act of harvesting tinsila also served an ecological function. The digging aerated the soil and helped disperse the seeds, essentially cultivating the wild prairie. Another vital plant is the chokecherry, Prunus virginiana. Found in the wetter draws and gullies, this shrub produces tart, dark berries. These were pounded, pits and all, and mixed with dried bison meat and fat to create pemmican, a high-energy, preservation-stable food source essential for survival during the long Dakota winters. The interconnectivity of the ecosystem is evident here. The chokecherry relies on birds and mammals to spread its seeds, while the humans relied on the calorie-dense pemmican to survive the cold, which in turn allowed them to continue their cultural practices. The climate that necessitates such specific adaptations is defined by its continentality and the rain shadow effect. The Badlands are located in the geometric center of North America, far from the thermal inertia of any ocean. This results in rapid and extreme temperature fluctuations. The Black Hills to the west act as a barrier to moisture-laden air masses moving from the Pacific. As the air rises over the granite peaks of the hills, it cools and condenses, dropping its moisture as rain or snow. By the time the air descends onto the plains to the east, it is dry and warming. This rain shadow creates the semi-arid steppe climate of the Badlands. The average annual precipitation is low, but the evaporation rate is potentially very high. This moisture deficit is the primary stressor for all life in the park. The summer sun heats the light-colored clay formations, which reflect radiation but also absorb significant thermal energy, ground temperatures can exceed 140 degrees Fahrenheit. This intense heat creates localized convection currents. Air rises rapidly from the hot rocks, creating thermal columns that are utilized by soaring raptors like vultures and eagles, but also contributing to the turbulence of the atmosphere. The wind is a constant physical presence and a geological agent of significant power. In the winter, the region is subject to the polar jet stream, which can dip south and bring Arctic air masses that drop temperatures to 40 below zero. However, the region also experiences Chinook winds. These are warm, dry winds that descend the lee side of the mountain ranges to the west. As the air descends, it compresses and warms adiabatically. A Chinook can raise the temperature by tens of degrees in a matter of hours, melting the snow cover rapidly. This phenomenon is locally known as the, quote, snow eater. While this provides a reprieve from the cold for wildlife, it can also be dangerous. The rapid melt can expose plants to a sudden freeze if the wind shifts again, and it strips the insulating blanket of snow from the ground, allowing the frost to penetrate deeper into the soil profile. The wind also acts as a pruning shear for vegetation. Trees and shrubs in the Badlands often show a Krummholz effect, or flagging, where branches only grow on the leeward side of the trunk, protected from the desiccation and abrasion of the prevailing winds. The hydrological cycle in the Badlands is characterized by violence and scarcity. The soil, primarily composed of bentonite clay derived from volcanic ash, dictates the movement of water. Bentonite is a smectite clay, meaning its molecular structure allows water molecules to slot between the clay platelets. This causes the clay to swell significantly when wet. When a thunderstorm hits the Badlands, the first fraction of an inch of rain wets the surface, causing the clay to expand and seal off the pores of the soil. The surface becomes an impermeable barrier, almost like plastic. Consequently, subsequent rainfall cannot infiltrate the ground. Instead, it runs off immediately. This sheet wash is what scours the slopes and feeds the flash floods. It explains why the Badlands are so deeply eroded despite the low annual rainfall. The water does not soak in to weather the rock chemically from the inside, it smashes against the outside and carries it away. Conversely, as the clay dries, it shrinks, creating a web of deep cracks or popcorn texture. These cracks allow air to penetrate and break up the soil structure, preparing it for the next erosional event. This shrink-swell cycle creates a precarious footing for plants, tearing at root systems and preventing the establishment of slow-growing species. Within this harsh physical framework, distinct ecological zones or microhabitats emerge. One of the most fascinating is the slump block ecosystem. As the cliffs erode, large sections of the tableland sometimes detach and slide down the slope in a cohesive block, landing partway down the ravine. These slump blocks retain their cap of prairie sod. Because they are tilted backward toward the cliff face, they form a natural depression that catches water and sediment. These miniature basins often hold moisture longer than the surrounding Badlands, creating isolated pockets of lush vegetation. Here, one might find taller grasses, wild rose bushes, and even small pocket wetlands supporting amphibians like the Great Plains toad or the tiger salamander. These amphibians spend the dry months buried deep underground in a state of estivation, emerging only during heavy rains to breed in the ephemeral pools found in these slump blocks. The tadpoles must race against evaporation, metamorphosing into adults before their nursery dries up into a cracked mudflat. The biological soil crust is another critical, yet often overlooked, component of the Badlands ecosystem. In areas of the prairie that are undisturbed by hoof traffic, the soil surface is covered by a knobby, black or gray crust. This is a complex community of cyanobacteria, mosses, lichens, and fungi. The cyanobacteria are the architects of this crust. They secrete sticky polysaccharides that glue soil particles together. This biological glue stabilizes the soil against wind and water erosion. Furthermore, these organisms fix atmospheric nitrogen, converting it into a form that plants can use. In the nutrient-poor soils of the Badlands, this nitrogen input is vital for the growth of grasses. The crust also creates a rugose texture that traps seeds and pools water, increasing germination rates. However, this crust is incredibly fragile. A single human footprint can shatter the structure, which may take decades to regenerate. This is why staying on trails or walking in dry creek beds is emphasized for resource protection. The living skin of the prairie is the first line of defense against desertification. Among the specific faunal adaptations, the pronghorn, Antilocapra americana, represents an evolutionary puzzle. It is the fastest land animal in the Western Hemisphere, capable of speeds up to 60 miles per hour. However, no modern predator in the Badlands, not the coyote, the bobcat, or the mountain lion, can approach that speed. The pronghorn's speed is an anachronism, an adaptation to a predator that no longer exists, the American cheetah, Myricynonyx, which went extinct during the Pleistocene. The pronghorn is a ghost of evolution, running from a ghost. Its physiology is a marvel of engineering for speed and endurance. It possesses an oversized windpipe, huge lungs, and a large heart to maximize oxygen uptake. Its bones are light and strong, and its hooves have cartilaginous pads to absorb the shock of running on hard ground. In the Badlands, pronghorn are often seen on the open flats. Unlike deer, which rely on stealth and cover, pronghorn rely on their phenomenal eyesight and speed. They have a white rump patch that can be flared to signal danger to other members of the herd over miles of open distance. The relationship between the yucca plant, Yucca glauca, and the yucca moth, Tegeticula yuccacella, is a classic example of obligate mutualism found in the park. The Great Plains yucca, also known as soapweed, is a common sight on the dry, rocky slopes. It has tough, bayonet-like leaves and a tall spike of creamy white flowers. The yucca plant can only be pollinated by the yucca moth. No other insect can do the job. Conversely, the moth's larvae can only feed on the seeds of the yucca. In the cool of the evening, the female moth collects pollen from one flower, flies to another, and deliberately packs the pollen onto the stigma to ensure fertilization. She then lays her eggs inside the ovary of the flower. As the seeds develop, the moth larvae hatch and consume a portion of the seeds. It is a calculated trade-off. The plant sacrifices some of its potential offspring to the caterpillars in exchange for the guarantee of pollination for the rest. If the moth lays too many eggs, the plant can abort the flower, killing the larvae. This evolutionary check keeps the balance between the two species. The bird life of the Badlands includes species adapted to the verticality of the cliffs. The cliff swallow is a master mason of the avian world. These birds build gourd-shaped nests out of mud pellets, sticking them to the underside of overhangs and rock ledges. They require a specific consistency of mud, not too wet, not too dry, to construct their homes. They are colonial nesters, and their colonies can number in the hundreds. The constant traffic of swallows darting in and out of their nests creates a flurry of activity against the static rock walls. They are aerial insectivores, consuming vast quantities of mosquitoes and flies, acting as a natural pest control. Another aerial specialist is the white-throated swift. These birds are among the fastest flyers, capable of vertical dives at tremendous speeds. They nest in deep cracks in the rock, often in places completely inaccessible to predators. Their shrill, twittering calls cascade down from the high pinnacles, often the only sound heard in the deep canyons. On the ground, the western meadowlark is the voice of the prairie. Its flute-like song is distinct and carries far over the open grass. But the prairie also hosts more secretive birds like the sharp-tailed grouse. These birds are known for their lekking behavior. In the spring, males gather on traditional dancing grounds, or leks, to perform elaborate displays to attract females. They stomp their feet rapidly, rattle their tail feathers, and inflate purple air sacs on their necks, producing a low, hollow cooing sound. The location of these leks is often consistent for generations. The grouse rely on the mixed grass prairie for cover and food, eating buds, seeds, and insects. The encroachment of woody vegetation, often due to fire suppression, threatens their habitat as they require open horizons to spot predators. The reptile population utilizes the thermal properties of the Badlands to survive. The prairie rattlesnake, Crotalus viridis, is a pit viper, possessing heat-sensing pits located between the eye and the nostril. These organs allow the snake to detect the infrared radiation emitted by warm-blooded prey, such as mice or ground squirrels, even in total darkness. This is a crucial adaptation for hunting in the rodent burrows and crevices of the Badlands. During the winter, rattlesnakes congregate in communal dens, or hibernacula. These dens are usually located in deep fissures or slump blocks that extend below the frost line. Hundreds of snakes may share a single den, coiled together to conserve moisture and minimize exposure. They emerge in the spring, often sluggish and vulnerable until they can raise their body temperature. The park's roads absorb heat during the day and radiate it at night, unfortunately drawing snakes to the asphalt, where they are at risk of being run over. Insects in the Badlands are the unsung engines of the ecosystem. The dung beetle plays a critical role in nutrient cycling. With the reintroduction of bison, the volume of dung on the prairie has increased. Dung beetles break down this matter, burying it underground to feed their larvae. This action accelerates the return of nitrogen and phosphorus to the soil, reduces the breeding habitat for parasitic flies, and improves soil structure. Without these beetles, the prairie would be smothered in waste, and the nutrient loop would be broken. Harvester ants are another significant insect. They build large, conical mounds of gravel and clear the vegetation around them. Interestingly, paleontologists have a history of inspecting harvester ant mounds. The ants are collectors. They gather small pebbles to construct their mounds. In the fossil-rich soils of the Badlands, these pebbles often turn out to be tiny fossilized teeth and bones of micromammals, shrews, mice, and lizards that are otherwise incredibly difficult for humans to find. The ants effectively perform the initial screening for paleontologists, aggregating microfossils on the surface of their hills. The seasonal rhythm of the Badlands dictates the behavior of all its inhabitants. Spring is the season of birth and rapid growth. The bison calves are born in April and May, orange-red in color, contrasting with the dark brown of the adults. This is when the cool season grasses, like western wheatgrass, Pascopyrum smithii, do the majority of their growing. These grasses use the C3 photosynthetic pathway, which is efficient in cooler temperatures and lower light intensities. As summer approaches and temperatures climb, the C3 grasses go dormant, and the warm season grasses, like blue grama, Bouteloua gracilis, take over. These plants utilize the C4 pathway, which is more water efficient and functions better in high heat and intense sunlight. This succession of grasses ensures that there is forage available for grazers throughout the growing season, provided there is some moisture. Autumn in the Badlands is a time of preparation. The days shorten, and the light takes on a golden quality that accentuates the red layers of the Brule Formation. Animals enter a state of hyperphagia, eating constantly to build up fat reserves for the winter. The physiological changes are profound. The bison grow their thick, woolly undercoats, and the prairie dogs spend more time clipping grass to line their nesting chambers. It is also the rutting season for the ungulates. The clash of bighorn rams echoes off the canyon walls as they compete for dominance. This violent contest is strictly ritualized to prevent fatal injury, involving head-to-head collisions that are absorbed by reinforced skulls. Winter reveals the stark architecture of the park. With the vegetation stripped bare or covered in snow, the geological forms are the only features. The silence is profound. Survival becomes a matter of energy conservation. Many animals, like the badger and the skunk, enter a state of torpor, not true hibernation, but a deep sleep from which they can wake during warm spells. The bison face into the wind. Their massive shoulder hump is muscle mass that supports their head, allowing them to sweep aside snow to reach the cured grass beneath. The ecosystem slows down, waiting for the tilt of the earth to bring the sun back to the northern hemisphere. The Badlands also serve as a modern laboratory for studying the effects of light pollution and air quality. While remote, the park is not immune to the impacts of civilization. Air currents can carry pollutants from industrial centers hundreds of miles away, affecting visibility and the chemistry of the soil. The National Park Service monitors visibility as a key resource. On a clear day, the visibility in the Badlands can exceed 140 miles, allowing views of the Black Hills to the west. However, haze from sulfates and nitrates can reduce this significantly. The preservation of the viewshed is considered as important as the preservation of the land itself. The vast open horizon is a defining characteristic of the American West, and its obscuration represents a loss of wilderness character. The unique topography of the Badlands creates acoustic anomalies that are part of the visitor experience. The shape of the amphitheaters and canyons can focus sound, allowing a conversation to be heard clearly across a great distance, or conversely create sound shadows where the wind drowns out all noise. The soundscape is dominated by natural frequencies, the low frequency of the wind, the high frequency of insect buzz, the mid-range of bird calls. The absence of anthropogenic mechanical noise allows these natural sounds to occupy their full bandwidth. For the Lakota, this acoustic environment is conducive to prayer and meditation, facilitating a connection with the spiritual world. Geologically, the park offers examples of mass wasting beyond just simple erosion. Landslides are common, particularly in the wet springs. The contact zone between the permeable caprock and the impermeable shale beneath creates a slip plane. When this interface becomes lubricated with water, entire hillsides can detach. This process is distinct from the particle-by-particle erosion of rain splash. It is a catastrophic event in the life of a hill, reshaping the drainage patterns instantly. These landslides expose fresh rock, resetting the clock for soil formation and plant succession. The chaotic terrain of the landslide deposit, with its jumbled blocks of earth and rock, creates a distinct microtopography that is often colonized by pioneer species of plants that specialize in disturbed ground, such as the gumweed. The accumulation of selenium in the soil is a specific geochemical hazard in the region. Selenium is a naturally occurring element derived from the Cretaceous shales. In small amounts, it is a micronutrient, but in high concentrations, it is toxic. Certain plants known as selenium accumulators, such as the prince's plume and some species of astragalus, locoweed, absorb this element from the soil and concentrate it in their tissues. These plants often have a distinct garlic-like odor due to the volatile selenium compounds. If livestock or wildlife consume these plants in large quantities, they can suffer from selenium poisoning or alkali disease, which causes hoof deformities and hair loss. This is a chemical defense mechanism for the plants, deterring herbivory, but it creates a minefield for grazers. Experienced animals generally avoid these plants, but in times of scarcity, they may be forced to eat them. The management of the bison herd involves genetic considerations. The Badlands herd is one of the few conservation herds that shows no evidence of cattle gene introgression. In the late 19th and early 20th centuries, many ranchers experimented with crossing bison and cattle, creating beefalo, and as a result, many modern bison herds carry cattle DNA. The Badlands herd serves as a genetic reservoir for the Pure Plains bison. Genetic diversity is maintained by occasionally exchanging animals with other national parks, such as Theodore Roosevelt National Park or Wind Cave National Park. This prevents inbreeding depression and ensures the long-term viability of the species. Roundups are conducted periodically to check the health of the animals and manage the population size to ensure it does not exceed the carrying capacity of the range. The intricate drainage patterns of the Badlands, viewed from above, resemble the branching patterns of blood vessels or the roots of a tree. This fractal geometry is a result of the uniform resistance of the clay to erosion. Because the material is relatively homogeneous, the water follows the path of steepest descent, branching again and again to drain the area efficiently. This dendritic drainage pattern is a classic study in geomorphology. In the Sage Creek wilderness, the stream meanders, creating oxbow loops and cut banks. These cut banks are prime locations for spotting fossils, as the river slices through the layers. However, they are also hazardous, prone to collapse without warning. In the realm of microbiology, the Badlands offer extreme environments that interest astrobiologists. The conditions of high UV radiation, desiccation, and clay-rich soils are analogous to environments on Mars. Studying how microbes survive in the endolithic habitat, inside the rock pores, or in the cryptobiotic crusts, helps scientists understand the potential limits of life on other planets. The ability of these organisms to enter a state of cryptobiosis, effectively halting their metabolism until conditions improve, is a survival strategy that has allowed life to persist here through glacial cycles and interglacial droughts. The cultural connection extends to the use of fossils by indigenous peoples long before Western science labeled them. The Lakota had their own interpretations of the giant bones they found weathering out of the earth. They referred to the large fossils as the bones of the Unktehi, mythical water monsters that were destroyed by the thunder beings. This oral history aligns remarkably well with the geological reality. The Unktehi, often associated with marine reptiles or large mammals, were indeed buried in the sediments of ancient seas and floodplains, and they are revealed by the storms, thunder beings, that erode the land. This convergence of mythology and geology shows that the observation of the natural world has always been a central part of the human experience in the Badlands, whether through the lens of spiritual narrative or empirical science. The land forces an engagement with the past, demanding an explanation for the strange forms and the bones of giants that litter the ground. To bridge the gap between the indigenous understanding of the Unktehi and the rigorous investigation of modern geology requires stepping back from the biological present and plunging into the deep time of the Cretaceous and Paleogene periods. The bones that the Lakota revered as water monsters are indeed the keys to unlocking a narrative that spans tens of millions of years, a story written not in ink but in the stratification of mudstone, siltstone, and volcanic ash. The landscape that appears so static and impenetrable to the human eye is, in the geological sense, a fluid and chaotic record of continents colliding, seas rising and falling, and volcanoes erupting with cataclysmic force. To understand the Badlands is to understand the anatomy of North America itself. for the layers exposed in these canyon walls capture the very transformation of the continent from a flooded archipelago to the solid landmass we recognize today. The geological story of Badlands National Park begins long before the deposition of the colorful cliffs that draw visitors today. It begins in the darkness of the Pierre Sea. Approximately 75 million years ago, the geography of North America was unrecognizable. The continent was bisected by the Western Interior Seaway, a vast, shallow inland ocean that stretched from the nascent Gulf of Mexico to the Arctic. This was not a deep abyssal ocean like the Pacific, but a warm, eperic sea, likely no more than 600 feet deep in most places. The sea floor was a flat, monotonous expanse of soft, black mud. This mud was accumulating in an anoxic environment, where oxygen levels were low enough to prevent the rapid decay of organic matter. As dead algae, plankton, and marine creatures sank to the bottom, they were entombed in this black sludge. Over millions of years, the weight of the overlying water and subsequent sediment compressed this mud into the Pierre Shale. The Pierre Shale is the basement rock of the Badlands. It is the dark, slate-gray foundation upon which the more famous, colorful layers rest. Exploring the exposures of Pierre Shale in the lower elevations of the park reveals a world of stark chemistry and ancient biology. The black color of the shale derives from its high organic carbon content. Because the environment was oxygen poor, the organic carbon was preserved rather than oxidized. This depositional environment also facilitated the formation of pyrite, or fool's gold. Iron dissolved in the seawater reacted with hydrogen sulfide produced by bacteria in the mud to form iron sulfide crystals. Today, when the Pierre Shale is exposed to the atmosphere, this pyrite oxidizes, creating sulfuric acid and precipitating yellow sulfur minerals and gypsum crystals that sparkle on the surface of the black mounds. This chemical reaction makes the soil derived from the Pierre Shale extremely acidic and hostile to plant life, creating shale barrens where almost nothing can grow. The fossil record of the Pierre Shale is strictly marine, providing a stark contrast to the terrestrial mammals found in the layers above. This was the domain of the mosasaur, a sleek, predatory marine reptile that could grow up to 50 feet in length. Mosasaurs were not dinosaurs. They were giant lizards, closely related to modern monitor lizards and snakes. They were the apex predators of the Cretaceous Seaway, feeding on fish, ammonites, and even smaller reptiles. The shale also yields the remains of plesiosaurs, identifiable by their long necks and paddle-like limbs, and huge sea turtles like the archelon, which possessed a leathery shell and spanned more than a dozen feet from flipper to flipper. Perhaps the most common fossils, however, are the invertebrates. Ammonites, with their coiled shells, and baculites, or walking sticks, which were uncoiled, straight-shelled cephalopods, filled the water column. The baculites are particularly useful to geologists as index fossils, because they evolved rapidly and had distinct shell patterns. They can be used to date the rock layers with high precision. The transition from this submarine world to a terrestrial one was driven by the Laramide orogeny, a mountain-building event of immense scale. Far to the west, the tectonic plates were colliding, forcing the oceanic plate beneath the North American plate. This compression buckled the Earth's crust, thrusting up the Rocky Mountains and the Black Hills. As the Black Hills rose, the land to the east was tilted and lifted above sea level. The Western Interior Seaway drained away, retreating to the north and south. This retreat did not happen overnight. It was a slow, pulsating withdrawal that left behind shoreline deposits and deltaic sands. However, in the specific locale of the Badlands, there is a significant gap in the record following the retreat of the sea. This gap is known as an unconformity. The unconformity between the Pierre Shale and the overlying terrestrial deposits represents a period of missing time, roughly 30 million years, where no rock was preserved. During this time, the seabed was exposed to the elements. It became dry land. Rain, wind, and chemical processes attacked the surface of the Pierre Shale. The upper layers of the shale were weathered into a deep soil horizon. This ancient soil, or paleosol, is what we now call the yellow mounds. The vibrant yellow, orange, and purple hues of the yellow mounds are the result of intense chemical weathering known as patagenesis. The climate was hot and humid, likely similar to the modern Amazon basin. This heat and moisture caused the iron minerals in the soil to oxidize and hydrate, turning into limonite, yellow, and hematite, red. The yellow mounds are, in essence, a fossilized tropical soil developed on top of a Cretaceous seabed. This contact zone is one of the most visually striking boundaries in the park, marking the definitive end of the age of reptiles and the beginning of the age of mammals. Resting atop the weathered surface of the yellow mounds is the Chadron Formation, the oldest sedimentary unit of the White River Group. Deposited during the late Eocene, roughly 37 to 34 million years ago, the Chadron tells the story of a landscape becoming a floodplain. The Black Hills, now high mountains to the west, were eroding. Fast-moving streams carried gravel, sand, and silt down from the granite peaks and spread them out across the plains. The climate was still subtropical, but was beginning to cool slightly. The Chadron Formation is characterized by its haystack erosional forms, rounded, hummocky hills that differ significantly from the sharp spires of the layers above. The rock here is largely light gray to olive green mudstone. The depositional energy of the Chadron was variable. At the base of the formation, one often finds coarse conglomerates, rocks made of rounded pebbles cemented together. These represent the channels of ancient rivers that flowed with significant force. These river channels meandered across the landscape, constantly shifting their course. When a river changed its path, it left behind its old channel filled with sand and gravel. Over millions of years, this sand hardened into sandstone. Because sandstone is more resistant to erosion than the surrounding mudstone, these ancient riverbeds now stand out as winding ridges in the landscape, a phenomenon known as inverted topography. The soft floodplain muds have washed away, leaving the river bottom elevated as a stone snake winding across the Badlands. The biological context of the Chadron Formation is defined by the Titanothere, or Brontothere. These massive beasts are the signature fossil of this layer. To the early paleontologists, the Chadron was known as the Titanothere beds. These animals were perissodactyls, or odd-toed ungulates, distantly related to horses and rhinos. They stood 8 feet tall at the shoulder and possessed a bizarre, Y-shaped horn protruding from their nose. The presence of Titanotheres, along with fossils of primitive tapirs and rhinoceroses, indicates a lush environment with ample soft vegetation. The discovery of fossilized alligator scutes in the Chadron provides definitive proof of the wet, frost-free climate of the Eocene. These cold-blooded archosaurs could not have survived in a region with freezing winters, suggesting that the Badlands of 35 million years ago had a climate analogous to the modern Gulf Coast. A critical geological component that begins to appear in the Chadron and intensifies in the overlying layers is volcanic ash. This ash did not originate from the Black Hills, which are granitic uplifts, but from the Great Basin of Nevada and Utah. During the Eocene and Oligocene, the western United States was the site of the Ignimbrite flare-up, a period of intense explosive volcanism. Supervolcanoes, dwarfing the modern Yellowstone caldera, erupted thousands of cubic miles of ash into the stratosphere. The prevailing westerly winds carried this ash across the continent, where it settled like snow over the Dakotas. In some instances, the ash fell directly into the lakes and marshes. In others, it was washed into the lowlands by streams. This volcanic ash is a secret ingredient of the Badlands geology. Ash is composed of tiny shards of glass, obsidian essentially. Volcanic glass is chemically unstable. When it is exposed to groundwater, it devitrifies. The glass structure breaks down and recrystallizes into clay minerals, specifically smectite or montmorillonite. This bentonite clay is the defining structural material of the park. It gives the Badlands their popcorn surface texture and their incredible erosional dynamism. The transformation of airborne glass shards into sticky, swelling clay is a process of diagenesis that binds the history of Nevada's volcanoes to the erosion rates of South Dakota. Without this specific mineralogy, the steep slopes and sharp pinnacles would not exist in their current form. The land would erode more like a typical rounded hill. Moving up the stratigraphic column, we encounter the Brule Formation, deposited during the Oligocene epoch from 34 to 30 million years ago. The transition from the Chadron to the Brule marks a significant climatic shift known as the Eocene-Oligocene transition, EOT. This was a period of global cooling and drying. The polar ice caps were beginning to form in Antarctica, changing global ocean currents and atmospheric circulation. In the Badlands, the lush subtropical forests of the Chadron gave way to a drier, cooler savanna. The depositional environment changed from a system dominated by meandering rivers to one dominated by slow-moving streams and increasing amounts of windblown dust, or loess. The Brule Formation is the most scenic and recognizable part of the park. It forms the steep, banded cliffs of the Badlands Wall. The banding is a result of alternating sedimentary cycles. The reddish-brown bands are mudstones, representing periods of stable soil formation on a floodplain. The lighter tan bands are often siltstones or nodules of calcrete, calcium carbonate, representing drier periods or episodic flooding events. These bands can be read like tree rings, recording the pulse of the ancient climate. The regularity of the bands suggests a cyclical control on the climate, possibly related to Milankovitch cycles, variations in the Earth's orbit and tilt that affect the amount of solar radiation reaching the surface. Within the Brule Formation, there are distinct members. The lower member is the Orellin, or the scenic member. This is the classic turtle oreodont layer. The sheer abundance of fossils here is due to the nature of the deposition. The climate was dry, but prone to violent seasonal floods. Herds of oreodonts, sheep-sized mammals that looked like a cross between a pig and a camel, congregated around dwindling water sources during droughts. When the rains finally arrived, flash floods would sweep down from the hills, drowning the weakened animals and burying them rapidly in silt. This rapid burial is key to fossilization. It prevents scavenging and slows decomposition. The preservation in the Brule is often exceptional, with entire skeletons found articulated or joined together rather than scattered. The upper member of the Brule is the Whitneyan, or the pole-slide member. This layer is lighter in color and contains more wind-blown material, indicating a continued drying of the continent. The fossils here change as well. The large titanotheres of the Chadron are gone, having gone extinct at the climatic shift. They are replaced by animals better adapted to open spaces and tougher vegetation. We see the rise of the Lepticania, specialized oreodont, and the proliferation of horses like Mesohippus and Miohippus. These early horses were undergoing a rapid evolution of their limbs and teeth. As the forests receded and the grasslands, or open woodlands, expanded, the horses evolved longer legs for speed to escape predators in the open, and higher crowned teeth to grind the abrasive silica-rich grasses and wind-blown dust. One of the most enigmatic geological features found cutting through the Brule Formation are the clastic dikes. These are vertical walls of rock that intersect the horizontal layers, often protruding like ribs from the eroding cliffs. They are composed of sand and silt that is distinct from the surrounding mudstone. There are several theories regarding their formation. The most widely accepted theory involves sedimentary injection or infilling. One hypothesis suggests that as the sediments were drying, deep tension cracks opened up, essentially giant mud cracks. Sand from the overlying surface was then washed or blown into these cracks. Over time, this infill hardened into sandstone. Another, more dramatic hypothesis links them to seismic activity. It suggests that during earthquakes, pressurized slurry of sand and water from below was injected upward into fractures in the rock, similar to how magma forms a dike, but with cold sediment. The sheer number and grid-like arrangement of these dikes in the Badlands suggest a regional stress field, perhaps related to the ongoing adjustments of the Earth's crust following the uplift of the Black Hills. Above the Brule lies the Sharps Formation, the youngest major unit in the park, dating to the early Urartian, 30 to 28 million years ago. The Sharps consists of massive, light-colored siltstone and sandstone. It acts as the caprock for many of the formations. In geomorphology, a caprock is a harder, more resistant layer that sits on top of softer rock. It shields the column beneath it from rain. As the softer Brule mudstone erodes away from the sides, the Sharps caprock remains, creating the classic hoodoos, spires, and toadstools of the Badlands. Eventually, the caprock is undermined and topples, leading to the rapid destruction of the spire. This process is the primary mechanism of landscape retreat in the park. The erosional landscape of the Badlands is best understood as a retreating scarp. The Badlands Wall, or the Great Wall, is an escarpment that separates the lower prairie, the sod tables and the excavated valleys, from the upper prairie, the flat tablelands that have not yet been eroded. The wall is migrating northward. Every time it rains, a tiny fraction of the wall is washed away. The divide between the White River watershed to the south and the Bad River watershed to the north is constantly moving. The White River, flowing at a lower elevation, has a steeper gradient and more erosional power. Its tributaries are aggressively cutting back into the tableland, capturing the drainage of the upper prairie. This process, known as stream piracy, is one of the engines driving the expansion of the Badlands. Erosion in the Badlands operates through several distinct mechanisms. Rain splash is the most direct. The impact of a raindrop on the soft clay dislodges particles and throws them into the air, moving them downslope. Sheet wash occurs when the soil is saturated, and water flows as a thin film over the surface, carrying a load of fine sediment. But perhaps the most insidious form of erosion is piping. Because the bentonite clay shrinks and cracks, water can penetrate deep underground before it starts to flow. It travels through subsurface tunnels, eroding the rock from the inside out. Eventually, the roof of the tunnel collapses, creating a sinkhole or a blind gully. This is why hiking in the Badlands requires caution. The ground can literally be hollow beneath your feet. The landscape is also dotted with concretions. These are hard, spherical, or ovoid masses that form within the sedimentary layers. They are created by the precipitation of mineral cement, usually calcite or iron oxide, around a nucleus such as a leaf, a shell, or a bone. As groundwater flows through the sediment, it deposits these minerals in the pore spaces, gluing the grains together harder than the surrounding rock. When the soft rock erodes, the concretions weather out intact. In the Badlands, some concretions are enormous, forming large red boulders that litter the slopes of the yellow mounds. Others are small and hollow, lined with crystals. These are geodes. The breakdown of these concretions provides a lag deposit of hard rocks that armors the slopes and temporarily slows down erosion. The presence of chert and chalcedony in the park adds another layer to the geological narrative. These silica-rich rocks often formed in ancient freshwater limestone layers or as replacements of organic material. Chalcedony veins can be found cutting through the sediments. This material is extremely hard and breaks with a conchoidal, shell-like fracture, creating sharp edges. Indigenous peoples utilized this material for thousands of years to craft projectile points, knives, and scrapers. Geologically, the silica required to form these veins likely came from the dissolution of the volcanic ash. The groundwater became saturated with dissolved silica from the glass shards and reprecipitated it in fractures, creating a direct link between the distant volcanoes and the stone tools of the Paleo-Indians. Hydrologically, the Badlands are a study in ephemeral power. The primary architect of the valley is the White River. Its name derives from the high load of dissolved bentonite and volcanic ash it carries, which gives the water a milky white, opaque appearance. The White River is an underfit stream in some places, meaning the valley it occupies seems too large for the current size of the river. This suggests that in the past, during the melting of the Pleistocene ice sheets, which did not reach the Badlands but influenced the regional climate, the river carried significantly more water. The terraces above the current river level preserve the history of the river's downcutting. Each terrace represents a former floodplain, abandoned as the river sliced deeper into the bedrock in response to regional uplift or changes in sea level. The modern landscape is a snapshot of a process that is geologically rapid. The rate of erosion in the Badlands, often cited as roughly 1 inch per year on steep slopes, is incredibly fast. Most geological landscapes change imperceptibly over human lifetimes. The Badlands change visibly. A trail marker placed on a slope might be gone in a decade. This rapid erosion rate implies that the Badlands are a fleeting feature. They were born roughly 500,000 years ago, when the Cheyenne and White Rivers began their incision, and they will likely be gone in another 500,000 years, leveled to a flat plain. This transience is a sobering reminder of the power of water and gravity. The study of paleosols, fossil soils, within the park has become a sophisticated field of research. By analyzing the chemical composition of the ancient soils, specifically the isotopes of carbon and oxygen found in soil carbonates, scientists can reconstruct the ancient atmosphere. The ratio of carbon-12 to carbon-13 in the soil nodules tells us about the type of plants that were growing: C3 forest plants versus C4 prairie grasses. The oxygen isotopes can yield information about the temperature and the amount of rainfall. These geochemical proxies have confirmed the dramatic cooling trend of the Eocene-Oligocene transition. They show a world that was becoming more seasonal, with wetter winters and drier summers, setting the stage for the evolution of the modern grassland ecosystem. Within the stratigraphy, there are also marker beds. One such bed is the Rocky Fort Ash, located at the base of the Sharps Formation. This is a thick, brilliant white layer of relatively pure volcanic ash. Because it was deposited geologically instantaneously, in a matter of weeks or months during a massive eruptive phase, it serves as an isochron, a line of equal time. Wherever a geologist finds the Rockeford ash, they know they are looking at exactly the same moment in history. This allows for the correlation of rock layers across vast distances, connecting the geology of the Badlands to similar formations in Nebraska and Wyoming. The structural geology of the region is relatively quiet compared to the active faulting of California, but it is not devoid of features. The layers are generally horizontal, but they have a slight dip to the southeast. There are subtle undulations and minor faults caused by the settling of the sediments and the solution of underlying salt beds. In some areas, the dissolving of gypsum or salt deep underground has caused the overlying rocks to collapse, creating solution subsidence features. These add a layer of complexity to the local topography, creating erratic dips and jumbled layers that can confuse the casual observer. One specific erosional form that garners attention is the, quote, sod table. These are islands of the prairie that have been isolated by the circumvallation of erosion. The mechanism of their formation is a race between the tough, root-bound sod at the surface and the crumbling clay beneath. The roots of the prairie grasses, wheatgrass, blue grama, and buffalo grass form a dense mat that is incredibly resistant to rain splash. The sod cap protects the soil immediately beneath it. However, on the vertical sides of the table, the soft rock is exposed. Erosion undercuts the sod, creating an overhang. Eventually, the overhang becomes too heavy and collapses, dropping a block of sod into the gully. This process keeps the sides of the table vertical while the surface area slowly shrinks. The visual impact of the geology is heavily influenced by the angle of the sun. The texture of the Badlands is fractal. The same patterns of ridges and gullies are repeated at every scale, from a mountain-sized butte to a microscopic clump of clay. This self-similarity is characteristic of chaotic systems shaped by fluid dynamics. When the sun is low, the shadows reveal this intricate texture, showing the thousands of tiny rills that channel the water. These rills are the capillaries of the landscape, the first stage of the drainage network that eventually feeds the Missouri and Mississippi rivers. Even the colors of the rocks have a chemical story. The red layers are colored by hematite. Iron 3 oxide, Fe_2O_3 iron 3 oxide, indicating drier, oxidizing conditions where iron rusted. The green layers often contain chlorite or reduced iron, Fe2 plus Fe2 plus Fe2 plus, suggesting wetter, reducing conditions in a swamp or standing water. The white layers are often rich in volcanic ash or calcrete. The interplay of these colors is not random. It is a chemical logbook of the changing environment. During the Brule deposition, the alternation of red and tan suggests a climate that fluctuated between wet and dry cycles, possibly pulsing with the rhythms of the Earth's orbit. The preservation of trace fossils, or ichnofossils, adds another dimension to the rock record. It is not just bones that are preserved, it is behavior. In the mudstones, paleontologists find the preserved burrows of ancient insects and reptiles. Some burrows are simple tubes. Others are complex spiraling structures called demonelics, devil's corkscrews, found in related formations nearby. These were dug by the beaver-like paleocastor. While demonelics are more common in Nebraska, the Badlands contain abundant root traces, or rhizoliths. As ancient plants grew, their roots penetrated the sediment. After the plant died, the root rotted away, and the void was filled with mineral cement, or the soil around the root was cemented by the plant's respiration. These fossilized roots create branching, stony networks that preserve the structure of the ancient vegetation, proving that the barren rock was once a lush soil. Geologic hazards in the park are a reality of its formation. The same properties that make the bentonite interesting, its swell capacity, make it dangerous for infrastructure. The loop road requires constant engineering interventions. The roadbed is essentially floating on a sea of shifting clay. Landslides, or slumps, are common. A slump occurs when a coherent mass of rock slides down a curved surface. The hummocky terrain at the base of the cliffs is often old landslide debris. These unstable slopes make building trails or structures difficult, forcing the Park Service to adapt to the geology rather than trying to conquer it. The concept of the Badlands is, in itself, a geomorphic term used worldwide, not just a proper noun for this park. Badlands topography refers to any landscape with soft, sedimentary rock, sparse vegetation, and high drainage density. However, the South Dakota Badlands are the type locality, the standard against which all other badlands are measured. Whether in Alberta, Spain, or New Zealand, when geologists describe a badlands terrain, they are implicitly referencing the White River Group. This global significance elevates the park from a local curiosity to a fundamental geological standard. Finally, the geological history of the Badlands serves as a stark memento mori for mountain ranges. The sediment that makes up the park came from the erosion of the Black Hills and the Rocky Mountains. The very existence of the Badlands proves that mountains are transient. The granite core of the Black Hills is all that remains of a once much higher peak. The missing height of the mountains is spread out here, in the mudstones of the plains. And in turn, the Badlands themselves are being dismantled to feed the delta of the Mississippi. It is a conveyor belt of stone: uplift, erosion, deposition, uplift, and erosion again. The park captures the middle phase of this cycle, the moment when the deposited debris is being carved back into the void. This cyclical nature is the heartbeat of the planet, usually too slow to hear, but in the Badlands the beat is loud, fast, and visible.